Hey everyone, Nate here with Misbehavin'. Today I'm going to show you a piece of software that is free that'll allow you to make your own 3D models that you can then have printed, such as this tag. So let's get started. Okay, the first thing you'll need to do is download a program called SCAT. So we go to openscad.org and then click on Downloads. And then under the appropriate operating system for you, select the package. If you have Windows, you have your choice between 32-bit and 64-bit. The difference between these two columns is this one is an executable installer and will install to your machine. This one is a zip package. I recommend this one because when you download it and then open up the zip, the entire program is contained in a single folder. That folder can be run from a USB flash drive or even just your laptop hard drive, but you don't actually have to install the program. It makes it very convenient to remove it later if you choose not to use it. After you download it, open the program and we'll get started on the next steps. Okay, now that you've installed the OpenSCAD program, we're going to select New. And this is where we'll be creating our file. The code for the model will end up here in this side. This is our preview window for any CAD that we've already defined. It'll pop up as a 3D object. The console down here is where it will display any error checking or errors that it found in our code when we actually run it. And then the customizer over here, this is for parameters that allow you to define easy areas to type in information that automatically populate over here in your code. In the code for this tag, there's actually a parameter over here called name, and anything you type there is the words that end up in the tag itself. So what are we going to be creating? Well, what we're going to be creating is this tag here. So this is meant, I started using it to put the names of my hives on the bee boxes. So type in a name, 3D print it, and then screw it to the front of each of my beehives. And I realized other people might want to know how to do this and or at least learn the software, or at least learn it exists, and get a little practice in it. The thing I like about SCAD is that it requires you to program as well as learn to model. Now, I will say this is not the most efficient method for creating a 3D model, but it's free and it is accessible, I guess we'd say. And it teaches you basics of two skills. So this code is pretty complex. We are not going to actually program all of it. I'm going to take you through a few objects in the code, and then you can always just download mine, take it apart, follow the tutorials on the OpenSCAD website, and learn it for yourself. I will say that I downloaded and installed OpenSCAD, and then from never touching it before, programmed this model in about 45 minutes. So the learning curve, if you have a little experience, is not that bad. I would say if you're starting from scratch, it's going to maybe take you more like an afternoon. And once you learn it, I think you'll be moving right along. So one of the things you're going to be using a lot is, this is on the openscad.org website. In fact, let me show you exactly where it is. So we went to downloads originally. You click on documentation. This is the basic tutorials, very useful. They're kind of user manual. And then if you scroll down here to cheat sheet, this you'll be using a lot. I reference it almost every time I start a command. What we're going to start with today is called Polygon with points and paths. So what this is, we have to define this outer perimeter shape of our tag. So we're going to go ahead and, well, let's go File, New. Here's a new one. And let's just close down our old so we can't cheat. And then we are going to go here. And for Polygon, it's pretty basic, the programming language. You basically type in the word for the thing you want, and then you define what it does. Don't let this intimidate you. This is a simplified version of the code with abstracts holding the place of real information. I'll show you what that means in a few minutes. But basically for a polygon, we have to define the points for the corners or the vertices, and then tell the computer in what order to execute them. So this is at x0, y0. So that would be our first one, 0, 0. And then we'd repeat it for each one of these. And then we have to tell it, in this case, the example, it says P1, P2, P3. We could tell it to define 1, 2, 3, 4, and then it would go back to 0. And that gives us a box, and anything inside the box or inside the perimeter becomes a 3D object. But if we told it to go 1, 3, 2, 4, and then it would automatically default back to 0 for the next one, we would end up with a triangle here, and then another triangle down here. Not really what we intended. So back to our model, what we have to do is type in our basic information. Let's start with Polygon. There we go. And then we need to open a parenthesis, and then we type in points and an equal sign and 2 open square brackets. And then we're going to type in our points in X and Y for our perimeter. Now, I've already worked out, as you saw in the example code, all of this ahead of time. So I'm just going to type it in as it is in my code. You can follow along as I'll read it off. So it's going to be 0, 8, close, comma, open. And then this one is 0, 22, close, comma, open. And 8, 30, close, comma, open. 172, 30, close, comma, open. 180, 22, close, comma, open. And let's see, 180, 8, and then 172, 0, whoop, not 82, 172, 0. And then we have 8, 0, and then 2 brackets. So each set of brackets defines a variable, and then this last bracket closes off the set of XY coordinates. And then we're going to put a comma, and I'm going to put a space to make it readable. However, you don't have to add a space. The computer would read it the same. PATHS, paths, equal, and again, here we go, open 2 square brackets, and then we define the order in which we want it to read those points. So it's going to be 0, 1, and so forth. Now, a little note here on why it starts with 0. So we, as humans, don't usually think of things as being 0. Case in point, if you have an empty counter and you put an apple on the counter, you'd say there's 1 apple there. And then you go ahead and add another apple, it's 2 apples, and then 3 apples, and so forth. But the counter, when it was empty, was technically 0 apples. But we are able to think in abstract, which is 0 is nothing. Well, a computer can't define nothing, because in order to define something, it has to be something. It's a little counterintuitive to us because we take it for granted. But in the case of the computer, you have to start with something. So 0 is our something. We've defined this point right here as being 0, 0, 0 in the coordinate space. But then we automatically offset it with this one, saying no, our first something is going to be moved up to 8 on the Y, 0 on the X. So we've now redefined the 0 off of 0, but 0 is still 0, 0. So it's odd, but computers always start at 0. And binary is kind of the same way. Even when computers count in binary, it's always 0, the registers inside, and then they start counting up in binary. So 2, 3, 4, 5, 6, and 7. There are our points. 2 square brackets to close, comma, and then we have to define convexity. So convexity actually had me quite perplexed at first when I started programming in SCAT. But what it turns out it is a definition of how much resolution your model has. So in the case of what we just defined, which is a shape defined by flat sides, this actually can be a 1. That's the lowest resolution. If it were a circle, though, we would want that number to be fairly high. Think of it as in, are we going to define the diameter of a circle every 10 degrees or every 1 degree? The higher the convexity number, the more slices it makes out of the edge of a circle and defines it. A straight line doesn't need multiple slices. It just is a straight line. It's one slice. When it comes to our letters in this model, you'll want a fairly high number. And then of course here we've got to now come back to closing off our parentheses and adding a semicolon. Now if we execute this by clicking the preview button, we now have our basic perimeter. Now to demonstrate error checking here, I'm going to remove one of these and then execute. See, we get a highlighted line down here saying there's a syntax error in line 1. So we read along, it's saying that it's got an unexpected error here at the end of this section. So we know the error lies before where it highlighted. And we read along, and of course we know what the error was. We put it back in and preview, and we're good. So now our next goal is to create this shape slightly smaller. So we will end up just copying this line and bringing it down. That's one option. Or I'm going to cheat and go over to my code and actually just copy it over. So this has slightly different points defined for the same shape. They just bring it in a little bit smaller. Here's a quick note on how to add notes or comments to your code, or to be able to deactivate a line temporarily. Anytime you put in 2 forward slashes, anything that comes after it becomes a comment. And that means that the computer ignores it when reading, but you get to see it. That's a great way to add notes on what each line of your code is doing, add instructions on how to tweak it. Or in this case, we're going to deactivate this one and hit this preview button again. And we now get to see the smaller shape we drew, but originally we couldn't see it because it was inside the larger. All right, so now what we're going to do is called a linear extrude. So that is defined again in the cheat sheet. It's a 3D object, linear extrude, and you can read up on it if you need, but basically it allows us to take our 2D geometry and pull it any thickness we want in Z. For those of you new to CAD, this is the x-axis, this is the y-axis, and then the vertical is the z-axis. You see it here on this little trihedron. This little 3-point coordinate system is called a trihedron. It appears in most CAD programs, and it defines kind of the coordinates of your compass, you could say, within CAD. And as you see, when we go to rotate, it rotates with us. So it's a quick reference on which direction is which. All right, so we are going to type in linear underscore extrude and then open a bracket and type in height equals, and we're going to say 5. That's how many millimeters in the Z we want it to extrude. And you can put a space here or no space, that's up to you. But the next one is going to be center equals false. All right, so what this is saying is that when we go to extrude, are we going to extrude it based upon this being our origin? If we did, it would equally extrude in the positive Z and in the negative Z. If we say false, then it goes ahead and only protrudes in one direction. In this case, a +5, it's only going to go thick in 5 millimeters up, not 5 millimeters down. And then we type in convexity equals, I'm going to say 1. The resolution here doesn't matter very much because again it's straight line features. And then how many slices we want equals 20. This is how many slices it makes in the z-axis as it extrudes. This number can actually probably be very low too in this case. And then we want scale. And the scale equals 1.0 because we don't want it to change size. This would be another way we could go ahead and just extrude this exact line of code, basically copy and paste all of this down here, put this line for linear extrude above it, and then use the scale factor to shrink it. The way I chose with the actual coordinate points just makes it more absolute, whereas the scale factor could end up with kind of an arbitrary scale. That is, you wouldn't know, was it exactly 2 millimeters less on the points or whatever. And then our last feature is $FN equals 10. So this feature is how much resolution we want when it calculates the extrusion. It's optional, but it does add more smoothness to the features. And there is more information on that in the cheat sheet guide. So now we're going to go ahead and preview, and you can see we just extruded our small rectangle as compared to our, or not rectangles, box you could say, compared to our large one. All right, now when we finally get down to it, we need this same extrusion to happen to the first one as well. So we're going to say copy. We're going to paste it here. Now, I've already done the math. We actually want this to be 6 millimeters for the bottom one. And then so we can still see our smaller one, I'm going to make it 10. In a few minutes, that 10 won't matter so much, as long as these two are at least equal in size. All right, so now what we want to do is raise this inner one up a couple of millimeters, in this case 3 millimeters, to then when we subtract it from this one, we end up with a about 3 millimeter thick wall and a 3 millimeter thick bottom to this dish that we're going to be making. So the way we do that is called a translate. So anytime you want something to happen to something you've already created, you just put another line of code above it. And think of it as being an envelope inside an envelope. We wrote a letter, which is this Polygon feature here, and then we stuck it in an envelope that gave it this address, something to send it, something to do with it. But we also want that to be done, or something done with that letter. So we're going to put put all of this in the other envelope. So when the computer reads, it tears open this envelope, does the instructions, and then sends the letter on its way, and then tears open the envelope, does what it says, and then sends this on its way. And so it's kind of like peeling an onion in reverse for us when we program. So translate, and then open parentheses, V. The best I can tell, V stands for volume because these are 3D objects. So we're going to translate a volume in X, Y, and Z. So we're going to open now a square bracket. There we go, square bracket. We're going to say 0 in the X, 0 in the Y, but we want to raise it 3 in the Z, and then close the square bracket, and then close the parentheses. Now if we execute, watch what happens to our smaller shape. It just raised up. Now what we can't see is that it actually raised the bottom of it as well. So now we're down to the last step here on what we want to do with these two. We want it to take this shape and subtract this shape. That's called a difference. Now in programming and in 3D modeling, we have Boolean operations. They're logical operators. We have available here union, difference, and intersection. Union does exactly that. Two objects that touch each other that are put inside a union literally are merged together and seen by the computer as one object. Difference, just as in mathematics, take object A, subtract object B. And then intersection is a little different, where any two objects that are touching each other, it will only keep the geometry that actually overlaps. And anything that doesn't overlap gets taken away. That can end up with some very interesting shapes. Think of if you intersected two spheres and only the parts that actually were inside each other stayed behind. You'd end up with a very different shape. So when you start to play with intersections, you can add a whole new dimension to your geometry. But we are going to use difference. All right, there's difference, and then we've got to open and close a parentheses, and then I'm going to add a space and open a curly bracket, and then down here below everything we close the curly bracket to say that all of this happens inside of this difference command. And then watch what happens. There we go, folks. We just subtracted the bottom shape from the top, and we end up with this little dish that is the start of our tag. This is pretty much how this entire program works. And then you could actually add above this or after a line, you could type in some notes, and that would tell you what's going on, so you can note or annotate your code or comment it, as we say in programming. And then I like to leave empty spaces to break up my code, which you'll see in the example that I provide for building this tag. And it gets a little more complex. You eventually add the parameter over here so that you just type in your name and the tag updates automatically. But in the end, this whole screen right here of code defines this entire three-dimensional tag, which isn't too bad. So I'm going to demonstrate the parameter, and we're going to just add a 2 and enter. And as you can see, the code automatically updates and moves everything center. And there is our name 2. Now, when it comes time to create a 3D file, what you're going to want to do is go ahead and fully render. That's this button here. This one can take a minute. This goes and instead of generating a preview, every single line is calculated using the FN numbers and the convexity numbers. So it can take a minute, especially the more complex it becomes. And then you can go ahead and click STL. So STL, for those of you not familiar with 3D printing, is a stereolithography file. That is to say, it's all of the triangle trigonometry mathematics that define a 3D object. And that's what 3D printers these days usually use to make an object. So now that we just exported it, we can go here to our desktop, and I actually have an STL file. And if we open it, we get our nice little preview, and here is our tag ready for printing. So you could also send this off to a professional printer. You might have a friend that has a printer, or you might have one already. If not, I would suggest you try to find one. Most of the time now, they're getting very cheap. They're usually sub few $100s. Don't let the features confuse you. I would say most hobbyists can get by just fine with a printer that does not have a heated bed and that prints in a plastic called PLA. It's an organic plastic, which is pretty environmentally friendly. It doesn't hold up as well though to sun, so you're going to want to take this tag and spray paint it in order to let it hold up in the sunlight. Another plastic called ABS, think Lego bricks, is more stable, still yellows in the sun over time, but in order to print that, your printer will need a heated bed. And maybe later I can touch on that, but this is getting a little outside our norm for homesteading, but this definitely falls into the category of DIY. Well, I thank you for watching. If you've enjoyed it, please give the video a thumbs up, and subscribe to the channel if you want to see more how-tos, DIY, homesteading and farming, and the like. Thanks. Have a great day.